with riveting and soldering in horology for tonight. And this is two parts. Both parts will be tonight. They're both short parts, but need to split them so we don't have start having problems with the number of figures causing PowerPoint to malfunction. So here we go. Okay, so as a prologue, I think we all know that in horology we need to rivet. We've all probably had to do it if done any work on either movements or cases. And we'll go and discuss a little bit about how riveting works, provide a how-to guideline on proper riveting. Some of the material in this presentation came out of a workshop that we did. Wow, when was that? Back in 2018 or 2019. And it was a hands-on workshop. We actually, for the folks who were attending, they actually had a chance to practice some of these techniques, or at the very least see them done. So we'll try to, I've augmented this as well as I can with pictures so that folks, even though we can't be here to see it, if there's enough interest, we could do that that workshop again at some point. And along with that is soldering. Soldering is a tricky one because I don't like to say you should avoid soldering horology. I think the right word is minimize. And when you have to do it neatly and know when it makes sense, know when it doesn't. Always be aware that you're working with alloys of metals and you have to be sure that they match up properly with the type of material that you're actually trying to join or solder. And we'll talk about a few techniques along those lines as well. Now, when you're dealing with hammers, punches, and for that matter, unfamiliar alloys, it's always important to be safety conscious, whether it's using goggles to prevent fragments from flying off the hammer / punch when you strike them or whatever it might be. It's a good idea to be aware that things can happen when you're using either of these techniques. So in my opinion, anyhow, there's almost always a way to rivet if it comes down to a choice between riveting and soldering. And when you're inserting, say, for example, a rivet into a hole, that's a great opportunity to do riveting, but understanding that can't always happen. Rivets can often replace screws in many applications, although in many horological applications, particularly those that kind of originated in Europe, you can also sometimes see screws that are used as rivets. In other words, the screw would be inserted and tightened to the right point, and then the protruding end would be riveted down so that the screw could not back out. So you'll see that sometimes in certain clocks. In certain applications, soldering has advantages. There's times when you just simply cannot rivet and nothing else you try to do will work. So that's something that we have examples of those in this presentation that we can look at too. So to focus then on specifically on riveting, the trick there is it usually involves cold forming in some way. Again, you don't have to use screws and threads and taps. You can go right in and take care of the fit, properly fit it. And then with a few taps, you have a fastener that won't back out. So it has applications, and we've probably all seen what those various applications are, but we can see a couple examples here. Everyone knows that they've seen a clock with pillars that have been riveted. And sometimes those pillars come loose. It's good to know how to tighten them back up. Replacing wheels, balance staffs on watches, we'll see the rivet there. Of course, you think about riveting a balance staff. You don't think about beating away at the shoulder of that balance staff to rivet it down. So again, that goes towards proper technique to avoid damaging the things that you're trying to rivet together. And some other examples you can see here. We're going to talk more about these as we get into the presentation. But yeah, it's pretty much everywhere. Riveting is ubiquitous in horology. So the basic theory behind riveting is kind of interesting. It comes down to the compressive yield strength of the material that you're trying to use as the rivet, or rivet down to the mating surface. So either way, whether it's a actual rivet or whether it's something that a post and a plate or something that you're trying to rivet down or get fastened into a, say for example, a clock plate, you're going to have to deform or crush the material a little bit. Now, here's some interesting numbers. Brass has a compressive yield strength of 20,000 PSI and soft steel of 36,000. You would think it'd be much higher, but this is soft steel. So in order to get those kinds of forces, you've got to concentrate that force somehow. And say, for example, we have a 1 pound hammer and you're swinging it 3 inches down to the surface that you're trying to rivet. And say with each blow, you tend to deform the metal by 5,000. That's actually pretty aggressive. If you could do a 5,000 inch displacement on a rivet in 1 blow, you're doing a pretty heavy job there. But just for the sake of the numbers, you can see how they do the simple math on that. That comes out to about 600 pounds of force at an impact. Now, if you concentrate that down to about a 30-second diameter rivet head, boom, you got your 20,000 PSI. So you can see how the math kind of goes together here. And one of the corollaries that comes out of this is you're best to try to rivet in small blows and by spreading metal a little bit at a time, as opposed to trying to do it all at once. The more force you put on a single blow, the more chance you have of just plain deforming whatever it is, whatever the structure is that you're trying to get riveted down. And then you can actually make trouble for yourself if you deform the wrong place. So an example of that is a click rivet, where you're counting on a shoulder to give you the clearance so that the click itself can move underneath the rivet. And if you have if you go too tough on those hammer blows, you may end up deforming even more than just the rivet area on the back of that click. You might also deform the shoulder, and now you got problems. You got a locked up click. You end up having to take the whole thing apart and redo it. So small blows are much better than large. Brass is a lot easier to rivet, obviously. Most alloys of brass, it is. But one thing to be aware of with brass is if you try to displace it too much, you're going to end up work hardening it, and then you won't be able to get it to do what you want anymore. It'll be too hard. Sometimes you can use heat to soften it, but unfortunately, the downside of heat is it could do collateral damage. So that's not necessarily a good option if you overdo it. The best option is to plan the rivet so that you can displace just a little bit of metal to get what you want and not have to go crazy on the rivet to achieve your goal. Mild steel like 12014 is kind of a breeze to rivet. It flows nicely and can easily be riveted. But again, if you overdo it, you could crack it. So you have to be careful there. And frankly, in my opinion, you should use steel for click rivets ubiquitously. If you use brass, there's a little bit of an issue there with the strength of the material. So, and obviously for things like, if you look at, the hook in a barrel, it often takes the form of a rivet, and much better in terms of holding mainsprings back, obviously, than brass will ever be. So that's a really good example of steel being used with respect to a very high force application, like holding back a mainspring. And of course, there's other riveting examples all throughout the industry. Everybody knows about pop rivets. And there's solid aircraft rivets as well, and tools that are designed specifically for applications using those products. So, but that's kind of outside the scope of this. Just wanted to provide a little contrast. Fundamental technique, again, you have 2 mating parts. Typically, a good number to shoot for is somewhere between 8 and 15 thousandths of protrusion, as you can see there in the diagram on the right. Much more than that, and you're going to have to do a lot of work to even get that surface, the deforming surface, down to the metal in order to be able to get it to hold. So it's really critical how long that protrusion is. And so, kind of looking at the range there, shooting for 10 is about what I do generally, and usually have pretty good luck. But then, I mean, obviously, you've got to have a tight fit. If you've got to spread that metal just to get a tight fit, you're going to risk something going wrong. So it's good to start with a tight fit. And once you have a tight fit, you need a bench block or something softer than the rivet to use as a backup for it, so that you're deforming the head of the tail of the rivet and not the other side, the head of the rivet at the same time. So, you know, for example, if that material that you're using for a rivet is brass, then use a brass bench block, or even perhaps aluminum. If it's steel, then you can usually get away with brass and it's just fine. So, in fact, if it's steel, you might get away with a steel one too. It just depends on how hard the bench block is. So the idea is you don't want to deform the rivet head or whatever it might be. Say, for example, it's a post that a wheel rides on, you know, or perhaps, you know, the tail of a rack or something like that, where you're trying to fasten it's a situation where, for example, the rack post has come loose and you need to tighten it back down again. Then you have a steel part there and you need to figure out a way to back it up so that you can, you know, provide some force to the tail of it to get it to hold in better. So, and for hollow parts, obviously, one interesting way to approach it is to use a round punch to flare it. We'll show an example of that, followed by a flat drift punch, and you can just flatten that rivet out and get a good tight fit there. So some tools that come in handy, the watchmaker's conical punches are really good. Dapping and drift punches. One real strong recommendation is if you look at the dapping punch, you know that those are usually very highly polished balls, and there's lots of reasons why. Obviously, those dapping tools are used for a number of things, but one really important lesson you learn from that is whether it's the dapping tool, whether it's the ball peen hammer, whether it's the flat side of the hammer, whether it's a drift punch, it's a really good idea to polish the faces first, so that, you know, whatever impression, whatever the condition of the face of that tool is, it's going to impart itself onto the rivet or whatever the material is that you're trying to fasten down. And so if you do a nice job of cleaning up the tool you're using to hit the end of that rivet, you're going to end up with a nice looking job imparted, or nice looking finish imparted upon that the back of that rivet. So try to keep that in mind. It's worth the time to polish those up before you actually use them. So here's an example. What we had to do here was we had a verge fork. Everyone knows what a verge fork is. It's the thing that comes in contact with the pendulum rod and kind of keeps and transfers the power from the escapement down to the rod. So here we had to make one that was literally missing off the clock. So simple part to make. You just had to get dimensions right and tight. But here we had the rivet, because we have a flat piece and we don't just want to solder that, or for that matter, try to rivet that wire right into that small horseshoe there. So instead, what we did was we made a little collar for it, and we formed the collar like a rivet. And the first thing we did, since it's hollow, obviously, since it has to pass the wire from the verge. So we took a round punch, conical punch, and gave it a light tap, spread the metal, as you can see in the upper right. And then with a drift punch, a flat face drift punch, polished, we gave it one more tap. And what do you know? Now we've got a good strong joint. And then the solder was actually used to fasten the wire to the little collar, because it was really kind of tough to find any other way that could reliably hold it. And that just worked out great. Another example, the hour hand bushing. This was a rather odd set of hands. And so in bushing, it was obviously originally not from the clock that it was actually fitted to. So we ended up having to make a new bushing for it. And you could see the shoulder of that bushing here. You could see the split that was sawed. And when you flip it upside down, it protrudes just right here, about 10 thousandths, maybe a little bit more. So now we're all ready to go. It's a tight fit, and that's what we needed it to be. But one thing that was missing was a way to back up that bushing so that we could rivet it. And so the solution was simple. We just took a piece of scrap brass from a cutoff and drilled the hole just a little bigger than the size of that. Let's see if we can go back here and show just a little bit bigger than this diameter here on this bushing, and fit it in. And with one simple tap with a dapping punch, voila, we spread the metal around, and that is all it needed. It held it plenty tight, and it wasn't going to move. So it was very simple. And the good news here is your first shot at this riveting is the best shot you're ever going to get, because then after that you start work hardening, and then it gets more and more and more and more difficult to get the metal to spread and to get the success you need for a tight fit. So, and the key to that is getting that protrusion right. If it sticks out about 10 to 15 mils, that first shot will probably be a good one. If it sticks out much beyond that, then you may have a big problem. And, you know, it's just as bad if you go too light. If you're under, say, for example, 5 mils protruding, you may not get enough of a shoulder there protruding in order to get a successful joint. So it's pretty critical to get that protrusion right if you're going to do riveting. Third example we've got here is, here we have we're going to replace a pin on an armature from a self-winding clock. And you'll run into this in a number of other areas, not just this one. It's everywhere. So this is a very common one where you have a pin protruding that needs to be either tightened or replaced because of wear. So removing it's pretty simple. We simply put it in a stake just big enough to accommodate the pin, and then struck it with the right size drift punch, and out it came. Getting it back in, well, first you had to make a new one. Started with 93 stock, protruding 10 to 15 thousandths. Now here it's a little trickier because we don't have a shoulder upon which to rest the other side of this part. So what we did was we drilled a blind hole in this scrap brass that would just accommodate that pin. Now it has to be a little big because obviously you don't want it to get stuck in there. So if it's a 93, I probably used whatever the next drill size was, 95 or 96, and drilled it down to where 2/3 to 3/4 of that pin was buried in that block. And the idea there is so that it's held steady and vertical, and so that if the pin has any tendency to try to deflect or bend, it's held back by the brass and it keeps it straight. So there's a number of different things. It won't tend to bend on you or tend to deform if you take light blows and just a little displacement around the outside edge. Whereas if you slam it hard, you're going to need all the help you can get to keep that pin from deforming. So there's a little bit of, the obvious way to go here is to make it a tight fit and 10 to 15th protrusion, and just go around the outside of that, either with the ball peen or with whatever punch you happen to want to use, such as a drift punch. Just go around the outside edge and deform that metal just a little bit on the outside edge. If you try to get at it straight on with, 1 or 2 single blows, you're going to take a big chance of, first of all, not having a successful rivet, and worse yet, bending the pin and having it end up fastened in there and, kind of bent or deformed. So, but this worked out well, and you can see the finished assembly there. It's vertical and it's well riveted. And here's an example of a flat bushing. And here what we did was we removed the original bushing. We turned up a new one. We had about a 10 or 15 thousandths protrusion. And with the with a small drift punch, that in this case might have been around, it might even been 1/4 inch. It could have used a 1/4 inch diameter drift punch, or maybe 3/16. And we, at each spoke, we located the drift punch, used the brass block behind it, and a single very light tap at each one of these locations. And we had this part riveted very effectively. It was not coming out. And what the discussion about riveting would be complete without dealing with the topic of bushings. And on the left here, you see a main wheel bushing, slightly peened with a polished hammer. We actually did this exercise in one of our workshops, and you realized really quickly how easy this is if you go about it with very light taps and you have it dimensionally set so it's protruding just right. Now, unfortunately, with main wheel bushing, sometimes you're forced to have the protrusion to be a little bit more than you'd like, ideally, because there's a requirement for it as a result of the original dimensions of the bushing. So you got to look at that too sometimes. But here we were able to got it to a reasonable compromise and got a successful joint. And on the right is a simple plate bushing where a conical punch was used to drive it down and spread the metal and giving us a little bit of a rivet there. But again, it still has to be a tight fit to start with. So you cannot make up for a loose fit by hitting it harder. It just doesn't kind of work out very well. Okay, well, that's pretty much what we have on riveting. So let's jump over to the more interesting sometimes topic, which is kind of surrounded in science, technology, and technique, all kind of in one here. And that's soldering. So we're going to talk a little bit about the alloys, the tools, some guidelines, some techniques, some good and bad examples, and then try to wrap up. So here we go. Of course, here we have even more potential danger with solders, because you not only have the solder itself, the metal itself, which could have some rather hazardous materials in it, such as lead or cadmium, but in addition, you have to be careful not to breathe in the dust if you should find yourself abrading or sanding the finished joint for whatever reason. So you have to be careful of inhalation. You also have to be aware that the fluxes are irritants. They're irritants both when they're in solid or liquid states, as well as when they're in gaseous states, should they start to evaporate when you apply heat. So there's multiple sources of irritation if you're not careful. So always wash your hands thorough when you're done. Wear gloves when in use to prevent contact with your skin. And of course, eye protection is a really good idea too, because you don't want this stuff getting in your eyes. Nor do you want to touch your eyes after you've handled the fluxes. You end up with a little trouble there. So the kind of soldering we're talking about tonight is basically low temperature soldering. Now we know that there's some very, very interesting high temperature solders. We saw Jack Wood demonstrate an example of one such solder at our workshop. And that one we're going to talk about. That one very briefly. It melts at about 1,000 degrees. Not something that you want to be doing with low temperature torches. And on most materials, you would damage the substrate if you tried to use those temperatures anyhow. So we're focused tonight on the kind of low temperature stuff. In soft soldering, the filler metal is melted. That's the solder itself. The base metal, obviously not. That's quite different than brazing or welding, where the base metal actually takes part in the whole process as well. And if you weld, you melt the base metal and it fuses to another piece of sometimes similar, sometimes dissimilar metal. But after soldering, the joint is not stronger than the base materials, unlike welding. When you do a good weld joint, it's often quite near just as strong as the base metal. But nonetheless, soldering, soft soldering, low temperature soldering can be very useful in many applications. And we're not the first ones to try this. It's been around for quite some number of years as evidence of the use of solders that go back 5,000 years. So here are the main elements of soldering. First, a clean and oil-free surface, and that's often neglected. And we'll talk about how easy it is to neglect it. But the net of it is, if you try to solder something in horology without taking it apart and cleaning it first, what you're going to end up with is you're going to be fighting probably 100 years worth of oxidation and trapped cleaning solutions that have caused a certain degree of additional contamination as well as corrosion inside the joint. And so you never really get a good joint unless you disassemble, properly clean, and then reassemble and prepare that joint for soldering. And that's something to really keep in mind. You have to have compatible metals. They have to be compatible with the type of solder you're using. Not all solders work with all metals. And we'll talk a little bit about that as we get into this. And the same goes for fluxes. Not all fluxes work with all metals as well. So, but the flux generally is meant to chemically clean the surface. And what happens is the solder then follows the flux wherever it happens to go. And so if you do a good job of preparing the surface, the flux will actually more likely flow into the joint, allowing the solder to follow behind it and bond. So, and of course, we also need heat in order to do all this, and there's a number of different ways to apply heat. So just to talk a little bit about alloys first. Alloys are, the study of the alloys is like, we could be here for like 2 hours talking about alloys alone. But we're only going to touch on the alloys that we run across most commonly in doing this kind of work. And there's also this concept of eutectic, which sounds very technical, but it's super, super simple. And what eutectic means is if you mix multiple metals to get an alloy. That's the way it works. You usually mix them by heat, but there's also other methods. But okay, so you take a pot and you mix these two metals, you put them in the pot and you heat it up. The beauty of eutectic is that what happens is that it creates a material, a new material, an alloy that has a lower temperature, a lower melting temperature than either of the metals, either of the major metals or any of the metals in the case of multiples in the mix. So for example, this example on the right, pure tin melts at 232 degrees C, pure lead even higher yet at 327. Yet if you do a eutectic lead tin mix of 30% tin and 62%, I'm sorry, 30% tin and 70, how does that work? Am I saying that right? 62% and 37. So it's 62% tin and 37% lead. You end up with a temperature, melting temperature of about 180 degrees C, which is lower than the melting temperature of either of the base metals. That's what eutectic is all about. There's actually another advantage to it as well. And that is that the material, as you start to melt it, goes through this kind of phase where it gets soft and pasty, and it doesn't make a really good solder. But when you use it in the right formulation at this eutectic point, you eliminate that pasty phase. So now you go right from solid to liquid, and then as it's cooling, from liquid to solid. And that's what eutectic means. And it's really an optimization. When you have the alloy mixed right, you get this effect. So that's kind of how it works. We'll give them a few examples of that in a minute. Some other cool things that happen in the world of alloys. Adding silver generally tends to increase the strength, but unfortunately tends to raise melting temperature in most cases as well. With tin-based solders, adding silver increases, like you'd expect, increases the melting temp. Adding bismuth or indium lowers the melting temperature and improves the wettability. Well, what do I mean by wettability? What I mean is how resistant the solder is to balling up on the surface. So when it flows out and doesn't ball up, that means its wettability is optimized. High tin content is also, by the way, not preferred for dealing with gold and silver because it tends to pull the gold and silver away. So there's other formulations other than tin solders that are better for that. And just as a by the way, since we don't run into this very often, aluminum solder usually contains a reasonable percentage of zinc. And that's kind of the big difference. You'll see tin zinc, you'll see tin zinc aluminum solders, you see cadmium tin additives, which means these aluminum solders can get a little bit nasty if you're not careful. And the melting temperature goes up if it's aluminum solder and meant for aluminum only. And the fluxes sometimes end up a little bit hazardous too because they got some fluorine compounds in them that can have some negative consequences on us. So it's kind of, we don't do much with aluminum, with clocks, with horology in general, although I know there's a few times I've had to solder onto an aluminum bezel to solve a problem. So every so often we do have to deal with it. So here's the most interesting alloys. Lead tin, which is the one that we all know about. It's the one that's used most commonly. It had been used in electronics up to about something like 10 or 12 years ago, until the world decided that lead was no longer an acceptable compound to dump into landfills. And so that all moved away from lead tin, but it's still available. It's still a very, very good solder. It's eutectic. It has great wettability. You create great joints with it, and it's easy to buy, and it's still very common in the work we do in horology. And because we deal with so little of it, we're hardly doing a whole lot to hurt the environment. Then there's also bismuth tin. Now, bismuth tin, you probably don't hear much about that, but literally you could go on Amazon and buy a 1 pound block of bismuth tin that you can use to cast parts. And it's also a great solder too. It's considered eutectic. It's considered strong and oxidation resistant. Used in jewelry making and medical apps. As I said, you can also cast parts. It's non-toxic, which is kind of its leading advantage. It doesn't have lead, and bismuth's considered relatively safe. So next up on the list is indium tin. Behaves a lot like bismuth, a little bit less brittle, very low melting point. You could see here 118 C compared to the 180 in the most common solder that we're used to using. I have the part number here in case somebody wants to consider it. It's great for doing bezels around glass because you don't want to heat, a bezel a lot because you could cause it to darken. And it's a cosmetic part and it's near glass. All good reasons to keep the melting temperature low. And again, this mixture is also eutectic, so it's optimized for a low melting temperature. Heck, I don't know of any alloy that has a lower melting temperature than that one does. Now, as I said earlier, when the big trend years ago was to move away from using lead in electronics, and these other alloys started coming up, and there's a couple of real common ones, and one is tin, silver, copper, sometimes just known as by other names in the plumbing industry, like 96-4, it's called sometimes, for lead-free plumbing. And there's actually a 96-4 and a 95-5 for all you plumbing aficionados. 95-5 is the same, but is kind of the same. It's still a tin solder, but it has antimony instead of silver in the mix. And they both are considered safe around plumbing, and they are both eutectic, although the temperature it takes to get those to melt is a little higher and the joints don't end up being quite as pretty. You end up with a little bit of a grainy looking joint because the stuff just does not flow like good old lead tin did. So, and then we have this formulation 99.5.5 tin lead indium. And this is sometimes known in the catalogs as TIX solder. And I'm sure many of you have heard of that. It also comes with its own flux, although it claims it will work with any flux. And frankly, if you're going to use TIX solder, great. Just don't use the flux it comes in because the stuff is nasty. It tends to be a little bit brittle is my experience. So I don't use it a lot, even though it has a great melting temperature, 135. I guess if there have been applications where I have used it, but now, I mean, it's so easy to buy indium tin solder. I just kind of prefer that if I need a really low melting temp. And of course, we talked about the solder that Jack Wood demonstrated for the repair. I think it was rings he was having us make in the workshop. 1005 degrees C. It's silver, copper, zinc, very high mixture of silver. And copper and zinc a little less, but still, this is silver solder. The 2 stories up here, the 217 degrees C tin silver copper is not technically silver solder. It has such a low dose of silver that the net result does not behave much like silver, either in color or any of the other properties. So that's something that gets confused quite a bit. You have to be careful of that if you're selecting solder. You will not find a real silver solder that melts at low temperature. It's just not out there. So, and of course, solder formats, you can get solder in good old wire rolls. You can get it in solder paste. You can get it in solder paste with syringes. You can even get it in what's called preforms, which are small squares that come in handy sometimes, but a little bit harder to buy, but they're very commonly used in the electronic industry. So let's jump over here to part 2 and get started right away. Again, Dick, yes, the date's wrong. We'll get that fixed. So a little bit about solder fluxes, since it's very, very important to get the flux right. The technical term means flow, and the reason it's a perfect name because it's what allows you to do the soldering, and literally the solder will flow in the direction where the flux is. So what happens depends upon the alloy you're using and the materials you're actually soldering. So we'll look at examples. The other good thing about solder flux is the molten flux actually helps transfer the heat between the mating surfaces, which is really important. Because if you don't have that, then one part gets hot, the other part doesn't, and you don't get any kind of meaningful flow, and you get a weak joint. So some of the common materials that are used, and at elevated temperatures, you want to remove the oxides. So you're going to probably use some kind of an acid that's going to attack the oxide. And here's some examples. Ammonium chloride and zinc chloride are really common. I have seen those in almost every flux. You can also see examples of good fluxes in the electronics industry, and relevant to us too, made from rosin. Succinic acid is one that's common in electronics. Borax is for brazing. And then of course you also have additives in vehicles and things that kind of keep these all in suspension and solve other problems with that fluxes are meant to solve as well. So without flux, you will not get a soldered joint. And one of the reasons is because as you heat the surfaces, you'll get oxidation, and the solder will not follow an oxidized surface. It just doesn't work. The only time there is actually says only with flux, but there is a time when you're soldering. Sometimes when you're soldering precious metals that don't tend to oxidize, you can get a joint without flux. And that's sometimes used in certain electronics applications, but not so much in horology. But the other thing that the flux does for us in horology, it gives us strong, clean, shiny joints. Not grainy, weak things that fall apart on us. These are really, really strong joints if you use the right flux. And we talked for a minute about solder paste, which is just basically the flux mixed in with ground up solder. And it's very effective in certain situations. Some solders, actually stick solders or wire solders, actually have the flux inside. For years, years ago, we had this product called multi-core. You actually still buy it today, which actually has 5 cores. The idea was just to make sure that you had plenty of flux at the joint. The idea was to create a solder that required no additional flux. Now, unfortunately, in horology, there is no such thing as enough flux inside the solder. We almost always have to supplement it. So for horological work, we're soldering either brass and steel, or brass and brass, or steel and steel. And for those, we need a little bit more kick than we can get out of the flux that's actually contained inside the solder. But on the other hand, for electronics work, we would have enough flux within the wire usually. Certain applications require some augmentation, but never, if you're going to augment, should you ever use acid core solder in electronics or electrical work, because the residuals, no matter how hard you clean it, will eat the wire alive, and your joint will be gone before you know it. So there's liquid acid flux, there's paste flux. The liquid acid flux, frankly, I tend to avoid in horology because it's got a heavy dose of hydrochloric acid. It's very reactive. Concentrations are usually quite high of these various acids. You never seem to be able to clean it up, and it splatters everywhere when you heat it. Even the salts that are left behind after you've done the solder joint, after it's cooled, even the salts that are left behind are corrosive. And I've had joints that I've soldered with this stuff, even a day later, show signs of corrosion, and that just does not work for me. So I've moved away from this material for doing horological work. If you're soldering brass to brass, rosin flux, which is just basically pine tree oleo resin mixed with other materials. Alcohol glycols, for example, if it's in paste form, it's petrolatum, which is sometimes known as Vaseline. It literally is a mixture of these things, and it's very good with brass. It doesn't leave behind anything that's going to do much corrosion, and it's easy to clean off with ethyl acetate or alcohol. So it doesn't work real well on steel, though. So we need something with just a little bit more kick for steel. And here's an example on the left here. Again, for steel, I really would avoid liquid acid flux because of the hydrochloric acid. And I mentioned earlier TIX flux. Problem with TIX flux is it has a huge concentration of zinc sulfide. I'd recommend other things. Frankly, this material I show on the left here, bottom left, no corrode, is really good for pretty much everything. I've used it for brass. I've used it for steel. I've even used it to solder nickel. It's pretty effective and it's not really high concentration of, it's like half or a third the concentration of acids as some of these others, but it uses petrolatum. And one of the advantages of having petrolatum in it is you heat it, it prevents oxygen from getting to the surface of the base metals and keeps it from oxidizing. And you can usually see that where you don't have the no corrode. It literally creates, you can see the metal as you heat it start to oxidize around it, but where the no corrode is, it doesn't. So for all those reasons, this no corrode is really great stuff. I've never had a corrosion problem with it. Cleans up very quickly. It doesn't have any hydrochloric acid in it either, which is really very, so if you remember one thing out of this, just remember no corrode. And if you remember two things, remember rosin paste flux, because they both come in handy and they're both mild enough, yet they have enough in the right application to do the job. So there's also this stuff called anti-flux, which keeps the flux from going in places it shouldn't. I really don't use it very much. If I want to heat something and have that transfer to the part that I'm trying to solder, I just use a really fine, thin of oil, and it seems to work just great. The reason I don't keep the anti-flux around is because if you've got it, you're going to pick it up and use the wrong thing, and you're going to end up with a mess. So I'd rather control the flux, and that gives me the control of where the solder goes. Personally, that's my preference anyhow. Some tools for doing soldering, you've got the typical soldering pencils, which give you point control of the heat. Torches are great, but you really got to be careful with torches because you can overheat a part and burn the flux very easily. So you have to be careful on how you apply it. And another tool that comes in handy is a hot air dispenser tool, which I actually use for quite a bit of electronics and electromechanics stuff. Comes in handy. You don't really have to have one for most of what you'll probably do, but if there's times when nothing works better because it minimizes the heat and controls how far you end up going with the solder. The problem is that if you have a large part, it's really difficult to do anything with that. So for larger parts, the torch is great, and even the solder pencil for certain things where you want to concentrate heat in a small area, but you want it to spread out. We have an example at the end of what I'm talking about there. Fixturing, extra pair of hands is sometimes a good idea, and so always keep that in mind. The last thing you want when you're doing a solder joint is to have it move when it's cooling, because then you end up with what's called a cold solder joint, and they're usually pretty weak. Sometimes you got to remove solder. Two ways to do that are solder wick and a vacuum desoldering tool. Solder wick is just like a braid that's impregnated with a mild flux, and you lay that in between the solder pencil and the material you're trying to remove, and it tends to pull the solder into it by capillary action and cleans up really nice. Vacuum desoldering tool, basically you pump it down, and when you have the joint heated up, you push the button and the vacuum pulls the solder away. There's also some pretty fancy electronic or electrical tools that do the same thing. They're much more effective than the vacuum desoldering tool, but this tool can do a lot for you. It's a relatively inexpensive tool. So when do you solder and when don't you? Well, when you're making parts, it's probably the best time to solder because then everything's taken apart and clean. But you got to have a nice tight fitting joint because solder does not fill big gaps real well. If you start trying to fill big gaps, you're going to have a weak joint. If you have a situation where something is stressed in compression, solder will work very well. And when you can do it in a way to hide the soldered joint, it's even better. You never solder it when you're trying to repair an assembly without taking it apart first to clean the joint. If you do that, you will have a bad joint. There's just no way around it. If you can rivet it, don't solder it. If you have a loose joint, you got to figure out a way to make it tight or figure out another way to fasten it. And if you have something that's getting twisted, it's not a good time to solder either. So, and I have never found a situation where soldering the movement plates has gone well. So that's something to keep in mind. You need to apply too much heat and you can do a lot of collateral damage, and there's usually another way to do the fastening. So as far as what to do, let's just do a quick summary and we'll show some examples. Maximize the tight fit and surface area to give yourself a good strong joint. Disassemble and clean, reassemble, apply flux, and heat enough to get the solder to flow well. Don't heat the solder, but heat the part to be soldered. And usually the more massive side of the two is where you heat, because that's going to be the part, the more massive thing you're soldering to is going to be the thing that heats the slowest, and that's going to make it difficult to solder on. And sometimes you could end up burning the lighter weight part if you're not careful. So apply the heat to the more massive part, get it to heat, and then the solder will flow in. Always neutralize. Ultrasonic with ammoniate is a great idea because the ammoniated cleaning solution neutralizes acid. And sometimes it's a really good idea to brush vigorously with a brass brush to get every little trace of that flux out of there. So here's some examples. We talked about this one, I think, in our second last presentation 2 months ago, in making up this this new ratchet for our Telecron clock. What we did here is we made sure that the new ratchet and the disc fit tightly. Then we applied the flux just where we wanted the solder to go, which was just around the rim of this wheel. And then we put a couple of small fragments of solder there. We don't have to stand there with a stick of solder and dump tons of it in. All we need is a little fragment. And you would be surprised how far that little fragment goes. Then we heated the stump on which this part was laying. And remember, we put a slight film of oil there. And then when the temperature was right, in went that solder, and we had a nice, clean, beautiful joint. And that's what it looked like when we were all done and it was all cleaned up. So that's one example. This one came off of another firm, KentClocks.com in the UK. You can see on the left, he started out with a cracked tooth he needed to fix. So he just sheared away the bad part. It fit a new tooth tip. And the tooth actually goes a little bit into the wheel rim. You can see here in this outline. And the solder joint was performed, and then the part was cleaned up afterwards. You can hardly even tell that joint's there. And that's a nice clean job. Lots of examples of replacing teeth. Here's a barrel teeth I found on another UK site. And here, you're using the solder to provide rigidity, not so much to provide strength in shear. And because it really isn't good at that, it'll shear off. And so by using the dovetail approach, you get a nice strong joint, and all the solder does is keeps it steady and in place. It doesn't provide the strength that keeps it there. The dovetail does. And it acts more as a fill than anything. And you can see what a nice job he did and how that cleaned up. And that's a nice repair job. You can't even see the solder. So, and then of course, just to kind of give you a quick summary of the don'ts, please never ever solder a part inside a clock movement when it's assembled. That is going to cause no end of grief. And don't solder something that can be repaired some other way, like bushings. Don't rely on solder for strength, which you would be doing if you left too big a gap. And again, sometimes the anaerobic glues have their place. I mean, we've talked about those in the past, and sometimes they're easier to do. You don't have to heat the part. You don't have to discolor the part. I prefer never to use epoxy glues, just for the record. The reason being, some next poor soul puts the clock in the cleaning solution and the joint's gone. Because epoxy glues and ammoniated clock cleaning solution don't go together. So anaerobics don't seem to be affected by it, which is really kind of a good thing in the world of horology. Here's an example of a movement where someone decided to solder the verge, and you could see the mess it created. Parts are rusted all around it. Even if you look to the left and up in the top here, you can see the suspension spring is rusted. And this is all a result of soldering while the movement was assembled. So it's a nasty thing, and most likely this was done with acid flux, liquid acid core, or liquid acid flux. And the results are obvious. Another one, some of these came off of, I mean, I have seen some examples of these, but unfortunately never took pictures. So but there's plenty of folks out there who have, and they have pictures on their websites, and you're welcome to go look at their websites. The links are provided here of some examples of some real atrocities done with solder, very inappropriate atrocities. And these are examples of where you could have done the repair a different way. And here's another one. Now here what happened was somebody tried to butt join this broken bridge. And the problem is that there's lots of oil smeared around clocks. You know, cleaning solutions leave oxide films over the years, and there's just barriers that are very difficult to get through when you have an assembled part in a movement. And you see the result, the solder balled up, it didn't flow into the joint. This repair won't last 2 weeks. This was an interesting one. Let's take a wheel with broken teeth and solder it to a section of a wheel that's coincidentally the same pitch. And I don't like this myself. It is kind of a bad wheel tooth repair. I think you could have a much nicer job if you just focused on the particular teeth that were broken, or make a new wheel. But this is not what I would consider a good application for soldering. And of course, this one last bad example, and we'll move on to the next thing. But this one is just wrong for multiple reasons. But again, it does demonstrate what a mess can occur when you try to solder a part that without doing a thorough cleaning in such a way that the solder can flow, because it just balled up everywhere. The solder just didn't flow anywhere that it should have flowed. So a couple of closing slides here. I thought I'd also bring up some interesting products that I've run across over the years. If you're trying to solder aluminum and pot metal, this is a really good product. It's called Muggy Weld Super Alloy 1. It's not terribly expensive. It literally can bond aluminum to brass if you want to. It can bond stainless steel to copper. I mean, it can do quite a few things. It can repair and fill pits in pot metal. One caveat is pot metal is probably one of the most difficult materials to solder out there. And getting a solid joint with pot metal is a real trick, especially if the pot metal is old vintage pot metal. This stuff does the best job of everything I've seen, but it doesn't necessarily mean your success rate is going to be 100%. So always be aware when you're dealing with pot metal that you're going to have to really test that joint. If you're trying to fill pits with it, it works great for that. But do be aware too that this material contains 19% cadmium. Cadmium is considered a carcinogen. You don't want to breathe it. So if you've got to grind or sand this stuff when you're done, you've got to wear a dust mask. Keep this thing out of your body. And of course, if you can, use the material outside, because then the fumes from the flux, you won't have to be breathing those, sitting over your bench and having those fumes going into your body. And of course, wash your hands after handling these materials. But this could be a lifesaver. This could be the only thing that works in an application. How do you solder nickel and stainless steel? Well, nickel's not actually that bad. It's difficult to do with most fluxes, but no corrode seems to work really well at nickel. Even lead tin solder will work with nickel, so it's not terrible in terms of the alloys. It's more difficult in terms of the flux, so you've got to use no corrode. By the way, Stay Bright kit, this Stay Bright kit, I use the Stay Clean as an example of a flux you shouldn't use in horology. But if you're working with stainless steel for some reason, you don't have to worry about that, because the stainless steel is not going to corrode no matter what kind of salts are left behind. So it's a pretty good material for use if you're trying to do some kind of crazy stainless steel plumbing job. Kind of an interesting one. Lead-free plumbing solder is okay for stainless steel as well. 95.5 or 96.4, either one of those is effective. But you've got to use, with stainless steel, you've got to use a flux that has a really strong acidic base. And that's the Stay Clean is perfect for that. Now, one little tip I'll give you on buying these Stay Bright kits. Once you buy the kit, what happens is they got the Stay Clean flux, in this little container, and then they put the solder in on top of it. Once you take this kit apart and use it, do not put that solder back in there, because what will happen is over time, the Stay Clean the fumes from that will start to escape or exude around the lid. It's almost unavoidable, and it will make a hell of a mess of that solder. It just turns it into a corroded disaster. So the salts will form all over it, and it's a mess. You don't even want to be holding on to it and touching it at that point. So just kind of be aware of that if you buy this kit. Separate it, and you're welcome to keep the Stay Clean in that little container. You'll probably have to, because you don't want it leaking all over everything, but keep the solder out of it. One last thing I did want to show was this concept of tinning with soldering. And people sometimes ask what that is. Well, tinning is a really cool technique for joining two things when you only have two hands, which most of us do. So if you don't have a way to fixture, which quite often happens, say, for example, you want to put those little pesky retainer strips or retainer, I don't know what form they might take in a particular application around the bezel, but if you want to solder some of those little strips to a bezel in order to retain a glass, I don't know of a better way to do it than this. This works better than anything else I've tried. So the way this works is you basically flux and then apply the solder and spread the solder around on each of the surfaces you plan to join. Next, you apply a little more flux. So you notice I didn't clean this off because this rosin flux is still pretty good after the solder joint is complete. It can still be useful, but I augmented it. I put a little bit more on it, and then I just applied heat. You can see the point here. This little bit of solder is where I applied the heat with the soldering pencil. And it's important that there be a little solder there to transfer the heat from the tip of the pencil. But then as you're heating it, all of a sudden there reaches a point where there's enough heat and shoop, this thing just solders right together. And you get a nice, clean, solid joint. Now, you may have to use a toothpick or something to hold it down when you remove the solder pencil so that it doesn't shift. But you clean it up and look what you got on the right. It's beautiful, nice, beautiful joint. Works out. And can be more convenient, require less, fiddling and fixturing than anything else with this. So. And now that we're mentioning tinning and using the soldering pencil, important things to keep in mind with maintaining soldering pencils is tinning and wiping the tip. You've got to keep it clean. You've got to have something like a sponge, wet sponge to wipe it onto. With the tip wetted with solder, touch it to the surface to be soldered. It's important that a little bit of solder come in contact with whatever it is you're trying to heat, because without that, you won't be able to get a transfer of heat from the tip, that tiny tip of that pencil. Then you apply solder to the surface, not to the pencil, but to the surface at this point, and you allow the solder to flow in the joint. You remove the tip from the surface and allow it to cool. And this assumes that you have a way to fixture whatever it is, like you tie two wires together. This is the way it's done with soldering in electronics, or putting two wires together. So overall, it's kind of some concluding tips. Although we should minimize soldering in horology, it can be a very, very useful repair tool. If it's done with care and you leave it as invisible as possible. Sometimes, like with these dial retainer clips or strips, it's really hard to make them completely invisible, but using the tinning technique we just described, you can get pretty close. Always clean up regardless of where or what. Always clean up after the repair. Get all that acid out of there. And we have a part number here for 118 degrees C melting material, the indium tin solder for working around glass bezels. I've actually tried this stuff. The flux is rather sweet smelling. Other than that, it's not a whole lot different than working with lead tin solder. It flows well and produces a really strong, flexible joint. It's actually more flexible. Not to say it's weaker, it's just more flexible and resistant to cracking than lead tin. So has its advantages in addition to the low temperature. And that's what we've got tonight. Open the questions. I'm sure with all that material, there's got to be somebody who has a question.
I've got a question for you.
Yes, sir.
Since my computer went squiff and then came back again, muggy weld for pot metal.
Yes.
Okay, can you put that back on there so I can copy that down?
Oh, sure.
Okay.
Here, we'll take it up there for you.
Okay, there we go. All right.
Super Alloy 1. You go on their website, you can buy it right now. It's currently available.
All right, well, I was just,
And they also have videos on how to use this material too, which I would really suggest you watch, because even if you think you know how to solder, this stuff's tricky. It works real well, but it's just a little tricky. Their flux actually is designed to turn like the color of root beer when it's just right to apply the solder. So the temperature is real critical. If you go much above that, you'll burn the flux. And if you don't get it to that temperature, it's not going to be hot enough to get the solder to flow. So it takes a little bit of practice, but it works better on pot metal than anything I've ever seen.
well, old phonograph parts sometimes are made out of pot metal,
Yeah.
and that's a pain. So, when they crack or break.
Yeah.
So, okay.
Exactly what you mean.
Thank
It'd be
you.
handy for soldering around like the bezels on the older cars. I got an MG with that the taillights have that pot metal base to put the lens on, and I need to take those off and fill up all the holes so I can get them re-chromed.
Yep. That's exactly what this stuff is meant to be used for.
And how about some tips on properly tinning the iron?
Yeah, well, the first thing you have to make sure when you're tinning the iron is that the iron is relatively oxide free. And sometimes the only way to get it to be oxide free is if you use either a brass metal wool or even steel wool, and you brush it to kind of get all those oxides off of there. And once you see some sign that the thing is starting to become shiny, then you get the solder on it to kind of try to build up a layer of wet solder. And at that point, then you can use the pencil. But if you don't do that, you'll never be able to get it. It's useless because the oxide acts as such a heat barrier that you can't get it through to the base metal you're trying to solder. So the key there is just get that oxide off of there. Usually, if you use a temperature controlled tip, you don't have a lot of trouble with this because they keep the temperature of those tips so you can adjust it to where it's just right for a particular solder. But if for some reason that oxide forms, then yeah, you got to get it off of there heck, I mean, if it comes to it, you may have to use a very fine file to clean it off if it gets really nasty and heavy on there.
Radio Shack used to sell sort of a paste that you would dip the tip of the iron into. That I don't know what was in it, but it seemed to be used for tinning the iron. Any experience with that?
Yeah, it's kind of a flux, and it does work. I think could be a pretty nasty flux. But again, the first thing you're going to do is as soon as you get some sign that the tip is cleaning up, you're going to get a coat of solder on it. So, and with that action, you usually will remove that will in itself with a couple of wipings on the sponge will remove whatever residual there is of any salts from that material. So.
Ken, are these slides going to be available anywhere?
We are recording this, so this will be available on our NAWCC21 YouTube site. We'll put the link in the notes. I could put this up on my website too. I mean, that's also possible, just as a slide set if you'd like.
That would also be nice because it's easier to review them than go through a video.
Okay, I'll see about getting that up there. I want to check back in a week. Anyone else?
I've found that a carbon type resistance soldering tool is good for putting on those tabs, but you got to make sure that you get off the pedal on the thing before you pull it off, because otherwise you arc and you put a burn spot in your tab.
Yeah, then it gets to be, then it becomes an aesthetic issue, doesn't it?
It's like a little arc welder when you do that.
Yeah. Yeah, and it's really important with soldering that you don't overheat. I mean, you can so easily overheat flux that you got to be. So, you know, if you're thinking about, hey, I want to do a little more soldering or get a little better at it, the first thing you should consider is going out and getting a temperature regulated soldering pencil where you can set the temperature. That way, depending upon what solder you're using, I mean, if you just have a single temperature soldering pencil and you go to use the indium solder, you're wasting your time because it's going to heat it to 450 degrees or something, and it'll just burn the flux and burn the solder, and it'll just make a big mess. Whereas if you use a temperature controlled pencil, you could set the temperature to 300, 290 or 300 degrees, and you can use the indium solder, or you could set it to 380 degrees and you could use the lead tin solder or whatever, you know. And then you get your tip to last as long as it can last and minimize oxidation. And, you know, like the weller I show in this picture, this weller actually shuts off on its own if you leave it on and forget about it. And that's really great because it keeps your tip from turning into toast. And then, you know, if you leave it on and you forget about it, it just makes a mess, and it just almost, at some point, it just corrodes the tip away, and then you have to replace the tip. So having temperature control prevents all those issues, and having the auto shut off is another really good feature. So this little device here is not all that expensive, this weller device showed in this picture, and it's super handy.
Yeah, I used a Variac on mine for years, and then the other thing it's cheaper and readily available is a light control. The ones you use to turn, you know, the box you use to make your living room lights lighter or darker. You can put one of those into an electrical box and use it as a power control for a little soldering iron. That works fine.
Yeah, that works great. If you don't have this device, yeah, it takes a little trial and error to get the settings because you got to play around to see, you know, okay, at this setting, it doesn't really melt anything. And right here, a little more, it melts nicely. And that's kind of where you end up setting it. So a little trial and error. But yeah, that can work very, very well. Either one of those. Variac's more expensive. The light switch, the light dimmer idea works great. I mean, there's nothing wrong with that for heating elements. They're fantastic. So yeah, that's actually a great suggestion for folks that don't have a device that's particularly temperature regulated or settable, like that weller that's shown in the picture has.
To solder aluminum parts, do you need to clean aluminum oxide off the surface?
Yeah, with pretty much any soldering, you're going to need to clean every bit of oxide away. You're going to have to abrade it, and you know, Scotch-Brite works really well as an abrasive if you're trying to clean up prior to, you know, soldering aluminum. I mean, even stainless steel you've got to clean up. I mean, it's just stainless steel. Both stainless steel and aluminum have a bad habit of doing this thing that's called passivating. In other words, they form a layer that's impervious to, you know, any attempts to solder. So yeah, you've got to clean up first before you do anything, even with stainless. And that's one of the reasons why the fluxes that you use with those materials are a little bit more active. All right. Well, thank you everybody for your attendance and your good questions tonight. Appreciate it.
Thank you.
And I see we've got some visitors from Central Time because the clocks in the background say 10:30. So I appreciate all of your attendance, even those that are miles and miles away.
Thank you, Ken. Very nice.
Okay, folks, I hope you find it handy. I agree with the thought that this is one where it would do well as a reference. So we'll put it up on on my website.
Thanks a lot.
All right. Well, thank you guys again. Appreciate it. Until
Thank you,
next
Ken.
time. Okay.